This is the 1987 AIME problem number 3. By proper divisor of a natural number, we mean a positive integral divisor other than 1 in the number itself. A natural number greater than 1 will be called nice if it is equal to the product of its distinct proper divisors. What is the sum of the first 10 nice numbers? So let's try to find a couple of nice numbers. And by this we need to look at its prime factorization. So for example, one immediate choice would be, well, what if n is equal to p times q, where p and q are distinct primes? What will happen in this scenario? Well, we'll have proper divisors p and q, because 1 and pq are not proper by this definition. So this will give us proper divisors p and q, where if we are to multiply the proper divisors, we get pq, which is the criteria for being nice. Alright, let's go searching for more. So next thing we'd want to naturally try like a power of a prime, and we see that doing p cubed will yield proper divisors of p and p squared, where if we multiply we get p cubed, which is the criteria for nice. So we have two possible like general forms of nice numbers. So maybe I'll leave it to you as an exercise to see why like nothing else will work. I don't think it's too difficult. For example, let's see why n equals p to the n, where p is greater than or equal to 3 fails. P is greater than 3 fails. And then we can obviously see for p equals 1, p equals 2, this will not work. So p greater than 3, then we will have, what are the proper divisors of p to the n? Well, that would be p squared all the way until p to the n minus 1. So and then if we were to multiply these proper divisors, we get p, and then these are just 1 to n minus 1. We know there's a closed summation, n times n minus 1 over 2. And we want this equal to p to the n. So matching exponents and then reducing, we get n times n minus 1 is equal to 2n. Let's see, I'll maybe write it like 2n. So bringing the 2n over and factoring, we get n times n minus 3 is equal to 0. So 0 is obviously extraneous, and then n equals 3 is our only solution. And then I'll leave it up to you to generalize why this is the only other good form. Alright, so now that we have our two forms, let's go hunting for the 10 smallest, right? Because it says we need to find the smallest. Some of the first 10 nice numbers, yeah. So let's start with, we need to note that p and q are distinct, otherwise we'll have p squared, which is not nice. So we need to start with like 2 times 3, and then this is just like listing and constantly comparing. 2 times 5, 2 times 7 is okay. Let's see, and then we completely forgot about 2 cubed, which is 8, which will be like sandwiched in between these two. So 2 times 7, we have 3 times 5 maybe next. So next thing here over would be 27, 3 cubed, so we don't have to worry about that for a while. So 2 times 11 will be 22 versus 3 times 7, which is 21. So we'll just put 3 times 7 first. 3 times 7 followed by 2 times 11. Okay, and then 2 times 11, 2 times 13 versus, yeah, sure, so 2 times 13 followed by 3 to the third power. Now let's see how many numbers we're at. We're 1, 2, 3, 4, 5, 6, 7, 8, 9. So we need one more number. So after 2 times 13, we'll have 3 times 11. Right? Yeah, 3 times 11 followed by 2 times 17. So we have our 10 least smallest nice numbers. Let's add them up now. So we have 6 plus 10 plus 14 plus 15 plus 21 plus 22, 22 plus 26 plus 33 plus 8 plus 27. Great. So adding this will give us 16, 30, 45, 66, 88, 114, 147. 147 plus 35 would give us 182. And we are done.